So this video describes how to simulate this springy rigid body pendulum. So we have a rigid body, a 3D rigid body. It could really be any shape and have any moment of inertia uh, matrix or tensor. Uh, but for simplicity, let's just consider a cuboid. And we have a spring connected to some point fixed relative to the rigid body. It could really be any point, but here we are picking some corner point on the rigid body on the cuboid. And we have a massless linear spring connecting that point P to some point O on the ceiling, where let's say O is the origin. So how do we simulate or write equations of motion for a system like this? The free body diagram of a rigid body, pretty simple. We have gravity acting downwards, effectively about the center of mass point G, the spring producing a force from P to O, pulling on P toward O if the spring is stretched. These are the forces in vector notation. So we have some frame, some globally fixed frame here, fixed to the inertial frame. And of course, gravity is going to be in the negative z direction, z fixed. And this is the spring force, k times change in length, specifically the stretch, times the unit vector from P to O is how this spring force is going to be represented. So of course P, the point P where the spring connects to the rigid body, is fixed in a body fixed frame, and O is fixed in the global or inertial frame, right? So we can define some reference frames. I sort of prematurely define them here and use them here, but we can write some reference frames. The zero frame is inertial or fixed to the ground with z-axis vertical perpendicular to the ground. And then we have a body fixed frame that moves rigidly fixed to the body, which is what we're going to use to track the orientation of the rigid body. And like we discussed in a previous video, this system has six degrees of freedom, 3 translations and 3 rotations, because the spring itself, while it modifies the motion of the rigid body, it does not constrain it exactly, right? So there's a difference between constrain and modify. The configuration variables that we use to describe the motion are as follows. Configuration meaning position and orientation. That's what we mean by this word configuration. And the position we describe just using the center of mass variables, center of mass position x, y, z, represented in the zero frame. So essentially we are going to represent the position of the center of mass as the position relative to point O, the origin, and we are going to use the coordinates xg0, yg0, zg0 to represent this vector in the frame 0. Okay, so that's about position. But for orientation, we have lots of choices like we've discussed in the course. We're just going to use the rotation matrix Q that gives us the coordinates in the zero frame of any point S with respect to G, given that same point in the body fixed frame, right? So we are essentially using a rotation vector that transfers between your body fixed frame and your global frame for this relative position, right? So if you had some point S on this rigid body, the rotation matrix just tells us the position of that point relative to point G, right? So we are doing, for doing orientation, we are mostly thinking about relative motion relative to point G. And you can characterize that motion using the rotation matrix Q, right? So if this relative position of some point S relative to G is given by this coordinate, these coordinates in frame 0, you can get that at any point in time. You can get those coordinates by knowing this rotation matrix and essentially rotating the coordinates in the body fixed frame. Okay. The velocity state variables, namely the derivative of these things, are just derivative of those things. So we can go xg dot, yg dot, zg dot. Those are state variables as well. And then we also use the angular velocity components, omega x, omega y, omega z, but written in the B frame, the body fixed frame, because this is what is directly used in the Euler's equation. Right? Euler's equations are in this frame. Okay, so those are the velocity state variables. What are the equations of motion? Equations of motion are basically Newton's equation, or what's called linear momentum balance, which is just really another name for Newton's equation, or Newton's second law. Sum of all forces equals mass times acceleration. Acceleration is just this quantity, xg double dot, yg double dot, zg double dot, in the 0 frame. And then the sum of external forces is F spring plus F gravity. And we can write 3 differential equations by separating these components out as x double dot, y double dot, g double dot, 0, 0, 0 equals 1 over m sum of all external forces. When you write it like this, you want to make sure that this force is also converted into the 0 frame, right? So when you write this matrix on the left-hand side, you want to make sure that the thing on the right-hand side, the vector on the right-hand side, is represented in the same frame as this thing. You can really use any frame, but at least this equation is only true in an inertial frame, and we noted that this point O is in the inertial frame, and the 0 is an inertial frame. Okay, so that's about the linear motion of point G. For rotational motion or angular motion, we have the so-called Euler's equation or angular momentum balance. If you had a free spinning rigid body, all you have is dH with respect to G dt equals 0. If you have a rigid body with some external moments, then the right-hand side is just external moments about the point G. And then we can, just like in the previous lecture, we can write the angular momentum as essentially I times omega. Angular momentum equals I times omega, and we can choose to represent angular momentum in the frame B. So you have a diagonal moment of inertia matrix, because we almost always choose the body fixed frame as a principal axis frame so that the moment of inertia matrix is diagonal. So we choose that, and these are just going to be the moments of inertia of the cuboid. And this is the angular velocity in the B frame, represented in the B frame. The angular velocity itself is relative to the inertial frame, right? So this is very subtle. The angular velocity is relative to the inertial frame, but it's being represented in the B frame. Okay, it's a very important distinction. This is the angular velocity as seen from the inertial frame, but then we are choosing to represent that vector in the frame B. And then if you're going to write this equation with the left-hand side using the B frame, the right-hand side had better be also in the B frame. So we want to write the moments about point G and then convert it into the B frame. Okay. From the previous lecture, we have these equations of motion. These are the so-called Euler's equations. So this is what we use to simulate the free spinning rigid body, except now we have these 3 moment terms, which are external moments about the center of mass, represented in the point in the frame B. Okay, and the moments are of course basically R P with respect to G, where P is the point where the spring acts, crossed with the spring force at point P. Okay, so these are the Euler's equations. These are the Newton's equations. And then, just like the previous lecture, we can write ordinary differential equations for the rotation matrix itself. Dq by dt equals omega q, where omega is this matrix, this q-symmetric matrix, which of course depends on it's on the omega vector, but represented in frame 0, which you can get from the omega vector represented in frame B by doing this transformation. Okay. And finally, the initial condition. So we've just written a whole bunch of differential equations. These second-order differential equations, these first-order differential equations for angular velocity, essentially, and these first-order differential equations for angular position, or basically orientation, or in this case, the rotation matrix. We'll have to write initial conditions for everything. So we can write, well, whatever the initial conditions are: initial position of the center of mass, initial velocity of the center of mass, initial angular velocity, and initial orientation of the object, right? The initial orientation, of course, needs to be a rotation matrix, and should ideally represent the initial orientation of the rigid body. In the previous simulation, we may have assumed that the initial orientation is identity, which essentially means that the body fixed frame is identical to the inertial frame just initially. But of course, if you are simulating something like this, maybe you want it to be oriented in some weird direction initially, and you can achieve that by appropriately different rotation matrix, let's say. However that is given. So I'll let you guys think about it. So, but essentially we have these equations of motion, right? So these are 3 second-order differential equations, which is really 6 first-order differential equations, plus 3 more second-order differential equations, so 9 so far, and then 9 more first-order differential equations, a total of 18 differential equations, right? 18 ODEs. So it's actually a 6 DOF system. And the reason it's 18 is because we use rotation matrix. If we used something like Euler angles, 18 because we used rotation matrices, which is very redundant. If we used Euler angles instead, how many equations would we have? We would have 12 ODEs instead. Right? So because we would have essentially 6 ODEs for Euler angles and 6 ODEs for the position and velocity of G. We would essentially have 6 ODEs for the position and velocity of G total, and 6 ODEs for Euler angles and their rates. Okay, 12 ODEs. And it doesn't, depending on the situation, it may be better to use rotation matrices versus Euler angles. And we shall leave that to a future lecture or video.